Alright, now we're going to look at the two other methods of solving 2x2 systems. 2x2 systems meaning two equations, two variables. The first one we're going to do is the substitution method. Now we already did an example using the graphing method, and the graphing method, as I mentioned in the previous video, has a lot of good things about it and has a few bad things about it. And the bad thing being getting answers that are fractions and decimals. But that's not going to be a worry with either of these two methods. Both of these methods are going to get exact answers. Just don't get the picture of what's going on quite as readily. So I'm going to use the substitution method here, and then I'm going to use the addition method. Sometimes it's called the linear combination method or the elimination method on that example over here. And then the third one I'm going to do whatever method looks like it might work out the best. So in this case, unless the directions tell you that you have to use a particular method, it's kind of up to you. But I'm going to use the substitution method here. Now, the key to the substitution method is to take one of these two equations and isolate a variable. Because what you want to do is you want to make a substitution from one equation into the other. Now, if I take the top equation and I solve for x and try to isolate the variable x, I'd have to subtract 4y, then I'd have to divide by 3, and I'm going to get some fractions, which might slow down the algebra a little bit. If I solve for y in the top equation, I'd have to subtract 3x from both sides, divide by 4, fractions again. If I take the bottom equation, solve for y, let's say, I'd have to subtract x, and then I'd have to divide by -3. I'm going to get at least one fraction, which is a little better than the other equation, where I get 2. But this is the guy here. If I solve for x, the coefficient of x is 1. I'm not going to have to divide, and I'm not going to get a fraction. I'm going to go ahead and take the bottom equation and I'm going to solve for x. Now to solve for x here, all I'm going to have to do is add 3y to both sides. Kind of like solving a literal equation here. Just get the one variable all by itself. And I have x is equal to 6 plus 3y. This is key here. This is my guy right here. Because what I want to remind you of is that solutions to a system mean that there are ordered pairs that solve both equations. Whatever that ordered pair is, I'm going to plug the same x in here, the same y in here. I'm going to get equality for both equations. That means if in the bottom equation x is equal to this, in terms of y, it's equal to 6 plus 3y. In the top equation, it must be the same because I'm looking for that common solution. I'm looking for that common x. So I'm going to take this expression 6 plus 3y, I'm going to take the top equation now, I go back to the top equation, and I am going to substitute this in for the x in the other equation. I started with the bottom equation, I solved for x, now I take this expression and plug it into the top equation. Don't plug it back into the original, the one that you started with, because you're just going to get 0 equals 0. So in this case, if I make that substitution, and I'll try to color code this a little bit here, in for the x, I'm going to replace the x with 6 plus 3y. And then I'm going to write the rest of it, plus 4y is equal to 5. And I'm going to solve this, because now I've eliminated a variable. By substituting in, I only have the variable y. That's key. When you have two variables in the same equation, it's going to be near impossible to figure out what x and y is specifically. But by making the substitution, putting it exactly in terms of one variable, I can solve this for a value. I'm going to distribute. I get 18 plus 9y plus 4y is equal to 5. Combine like terms. 13y plus 18 is equal to 5. I'm going to subtract 18 from both sides. I'm running out of space here. I'll just go ahead and do some calculations. Divide by 13. I get y is -1. Now that means that my common solution that solves this system, it has a y value of -1. I know that my answer is something -1. I just need to find the x value that corresponds to it. Well, you know how to find the x. Given one of the coordinates, given the y coordinate, you plug back into either, or in this case, either equation. But my suggestion is plug it back in to the equation that you use for your substitution because the variable x is already isolated. That would give me x is equal to 6 plus 3 times y, which is negative 1. I get x is equal to 6 minus 3, which is 3. 3 goes right up there. That appears to be my answer. You can check your work by taking this ordered pair and plugging it into both equations. If it satisfies both equations, it's a good answer. And you can do it on paper. I'm just going to kind of do it in my head. 3 times 3, 9, plus 4 times negative 1, negative 4 equals 5. Yes, it does. 3 minus 3 times negative 1, that'd be 3 plus 3 equals 6. That's a good answer. Now over here, I'm going to use the addition method. And again, the addition method has a couple of other names. It's sometimes called the linear combination method or the elimination method. And the trick to the addition method is to use an algebraic property that says if A equals B and C equals D, then A plus C equals B plus D. I'm adding equal amounts to equal amounts and I get equality. I get equal amounts. Well, I'm going to first, for the addition method, write both equations in standard form. The x's and the y's on the same side. Now this one already has the x's and the y's on the same side, constant on the right. I'm going to have to rewrite this one a little bit by adding 2y. So I'm going to have 3x plus 2y equals 17 minus 2y plus 2y. I took this equation and I added 2y to both sides. That gives me 3x plus 2y is equal to 17. Now, I take the other equation, I'm going to put it right underneath it. Okay, now, remember back here I said I was going to add equal amounts to equal amounts? I'm going to add these left sides of the equation together, they're equal amounts, to these two right sides. These two expressions are equal, these two expressions are equal, therefore if I combine those and combine those, I get equality. However, I'm not going to do it yet because the idea of the addition or the elimination method is to eliminate a variable. I was able to do it back here with substitution. Here I'm going to do it with addition. But if I add the left sides, the x's don't cancel out, the y's don't cancel out. I'm not eliminating a variable. I need to kind of finagle one of these two equations. I'm going to have to set it up a little bit by being able to multiply both sides by the same non-zero number to set it up so that one of my variables will cancel out. Now, I have a plus here, I have a minus here for the y's. These are both positive. I like the fact that they're both negative, or opposite signs here. One's plus, one's minus, because when I add opposites, I'm going to get 0. Now, there is no nice, neat number that you can multiply by 2 to make it a positive 9. I mean 4.5. But I'm going to get all sorts of decimals. Instead, I'm going to look at these two numbers right here, and you should remember doing this back in your algebra days, and take the least common multiple of 2 and 9, which would be 18. I'm going to make this a positive 18y, I'm going to make this a negative 18y, so when I add the sides together, they'll cancel out. To do that, I'm going to multiply both sides, every term, by 9. 27x plus 18y equals 153, I think. I hope. Yeah, I think that's right. Down here, I'm going to multiply by 2. Now, you don't always have to do this. Sometimes it's already set up for you, or sometimes you only have to multiply one of the equations through by a number to set it up. And sometimes all the signs agree and you have to multiply one of the equations by a negative. But in this case, the signs were set up for me, just not the constants, not the coefficients. And so that's why I'm doing all this work. Now look what happens when I multiply both sides by 2. 4x minus 18y is equal to 2. Look at this. See how the 18y's are set? So now I use this property. I'm going to add the sides together. These are going to cancel out. I get 31x equals 155. If I divide both sides by 31, x turns out to be exactly 5. I know my answer is 5 something, because the x value is 5. Now, just like we did back in here with the substitution method, once you have one of the coordinates, you have to plug it back into either equation to solve for the other coordinate. It doesn't really matter, and I don't have, like at the convenience of the substitution one here, I don't have one of the equations all set up. I'll just take the top one. And it doesn't matter which one you take, and plug 5 in for x. So that'd be 2 times 5 minus 9y is equal to 1. So I get 10 minus 9y is equal to 1. I subtract 10 from both sides. I divide by negative 9, I get a positive 1. So I'm looking at this as my possible answer, 5 and 1. 10 minus 9 is 1. 15 equals 17 minus 2. Yep, that one's going to work out just fine. Both of these examples have a single ordered pair solution, so these are consistent and independent systems. Now my next example has got a little bit to it. I have fractions, I have parentheses. I think the first thing I'm going to do is I'm going to rewrite this. I'm going to distribute here. I have 2x minus 4y equals y plus 14. And then I'm going to subtract y from both sides to get the variables on the left side, put it in standard form. So if I subtract y, I'll get 2x minus 5y equals 14. Now this guy here, it's got the variables on the same side. I'm just not too crazy about those fractions. So the denominators are 2, 6, and 3. My least common denominator would be 6. I'm going to multiply through by 6 every term on both sides. So 6 times 1/2 x plus 76y equals 6 times negative 13 thirds. Distributing, I have 3x plus 7y is equal to negative 26. So the two equations with the asterisks are the ones that I'm going to use, and I'm going, because I've got them already have them in standard form, I'm going to use the addition method. Again, if I try to solve for x or y, I'm going to get some fractions, I'm going to get some fractions. I'm going to try the addition method. I have a feeling this one gives me some fractions anyway. But up here, I'm going to rewrite, I'm going to write this as 2x minus 5y equals 14. 3x plus 7y is equal to negative 26. Like the example before, I kind of like the y's because they have different signs here. I'm going to have to go for a least common multiple of 35, multiply this one by 7, and multiply this one by 5. So that's 14x minus 35y equals 98. And 15x plus 35y is equal to negative 130. Well, let's go ahead and let's add them up. Let's use this property here and add the equal sides to equal sides. These are going to cancel. I get 29x is equal to, looks like, negative 32. Oh, this is looking like this is going to be some serious arithmetic, because this is not going to come out evenly. If I divide both sides by 29, I have x is equal to negative 32 29ths. So my answer is negative 32 29ths something. Definitely not a problem to solve with graphing, because there's no way I would have graphed it and come up with negative 32 29ths as the x value of the point of intersection. Now, I have to take this guy and I have to plug back in. I think I will plug back into, it's about the same amount of work. Let's just take this guy here. 2 times negative 32 29ths minus 5y equals 14. So that's going to be negative 64 29ths minus 5y equals, now this is 14, which is the same as 14 over 1. I can see I'm going to have a common denominator of 29, so I better multiply 29 times 14. 6, 3, 11, 29. Looks like 60406. I'm going to write this as 406 29ths. I'm going to add 64 29ths to both sides. If I add a positive 64 to that, that's going to give me 470 29ths. And then I'm going to have to divide both sides by negative 5. Or better yet, let's think of this as multiplying by the reciprocal negative 1/5, since I already have a fraction here. So these are going to cancel out. I get y equals positive times negative is negative. 5 goes into that once. 5 goes into that 94 times. So I end up with a negative 94 29ths, which is a little bit, well, it's pretty close to negative 3. This is pretty close to negative 1. Now I think you would probably end up spending more time than I already have solving it if you decided to check this. By plugging these numbers in with all that arithmetic, you're going to be at it for a little bit. However, if you want to make sure you're doing it right, that's what you need to do. So you just kind of put up with it and plug in and do all the arithmetic with fractions.